compute the final color. And the dashboard starts after calculating the models and after rendering, computes the partial color gradients for each 2D Gaussian. And there are also gradient merger that accumulates these gradients for each unique Gaussian. And finally, the backward preprocessing transforms these 2D gradients back to 3D again. As our current work apply this powerful 3DS technology in many scenarios, our focus one of the most important applications, the SLAM, which is introduced by the former president. And the SLAM system contains two key modules: the tracking, which continuously estimates the sensor's real-time pulse, and mapping, which build and updates the consistent representation of the environment. And between these two, this mapping is not only critical for the final accuracy, but also more important than time-consuming, of course, for further acceleration. So, however, the training paradigm in 3GS SLAM is fundamentally different from the original 3GS. Compared to training on randomly selected images in the original 3GS, SLAM systems must process a continuous stream of images captured in sequence and optimize the scene with the sliding window. So this is where a performance bottleneck occurs. As our analysis shows, so the GPU failed to meet the 30 FPS real-time target with an approximately 10 times FPS gap. So, while there are already some review works about 3DS training acceleration, they do not address the specific challenge of the performance gap. So, GSR focuses on the offline training of the original 3DS, while GSPU does target SLAM, but it focuses more on the tracking mode. So there's a lack of accelerators for online training of the 3DS SLAM mapping process, and this is precisely where our work comes in. And next is the analysis and motivation. So first, we profile the training pipeline latency, and as the pie chart shows, the workload is highly distributed among stages, and no single stage dominates. And it shows that optimizing just one part will be enough, so a holistic optimization is essential. So we can optimize. We started analyzing the redundancy in the mapping process, and these images are heat maps of the per pixel training loss, where brighter means the higher loss, and as former president has already seen the redundancy in that, you can see that many areas are well optimized. So furthermore, of course, our SLAM processes continuous capture frames with only slight viewpoint changes. These high-loss areas exhibit strong spatial consistency. The difficult to learn features in one view will be difficult in the next, so making the loss map highly predictable. And another source of redundancy comes from the convergence over time. As the training progresses, the high-loss regions become even sparser, and you can also see in the graph that the loss distribution clearly converges. And this together brings us to our first key insight. The loss map shows strong spatial consistency across frames and convergence across iterations. And next, we found a major bottleneck in data flow. The original 3GS used a DSSM curve, which has a window-wise dependency. And the current curve implementation must wait for the entire image to be rendered. And as the time shows, this creates a synchronization delay and leads to a very low GPU utilization in loss computing. And fortunately, 3GS SLAM simplifies it and only uses the L1 loss. Based on the loss function, we find the gradient can be computed directly for each pixel. And this leads to our second insight. We can animate the explicit loss computing by leveraging the pixel-wise gradient independence. And finally, we found the fundamental data layout and access pattern mismatch. The pipeline constantly switches between the two cases, the Gaussian index and the pixel index. So for example, the sorting stage must group data by pixel index. As the diagram shows, result scattered non-continuous memory writes. And this problem reappears in the gradient merger. So this creates the offside problem, severe write contention, as multiple computer units try to update on the same gradient address. And this brings us to our third key insight. This constant during index switching highlights the necessity for special on-chip buffer to handle this reordering efficiently. And based on these insights, we developed our solutions. First, I will introduce our sparse algorithm design. For each mapping process, our algorithm starts with the common viewpoint first. We perform a full forward pass and to get an accurate loss map. And for next, we stack the top box with the highest error and perform sparse backward pass on them. But this leads to a critical question when we move to the next history keyframe. Do we still need to perform another expensive full forward pass? And based on our inside one, the answer is no. We know that we optimize areas can be predicted to start rendering the entire image again, which is the foundation of our algorithm. So here, the collage is the prediction is to use optimal flow. First, we take image from the current viewpoint and image from the last keyframe and compare the optical flow between them. And this gives us a future motion, showing how pixels have moved from one frame to the next. We then apply this vector vector to the loss mask from the previous keyframe and generate a predicted mask. And next, we apply this predicted mask to the forward pass, achieving also partial forward rendering, and subsequently the loss calculation and expensive backward pass are also performed sparsely based on the same mask. And within a single iteration, the entire process is repeated for the different keyframes. Finally, our algorithm is also convergence as well. To achieve this, we use a value-based threshold instead of a fixed sparsity ratio, and the threshold is set as a percentage of the maximum loss value. The benefit of this approach is that as training progresses and the model converges, the progressively increases sparsity and achieves even greater acceleration. And now, let's delve into the hardware design. To support our sparse algorithm efficiently, we co-designed dedicated accelerator called REACT3D. Here's the overall architecture of REACT3D, and let's have a quick overview of its modules. The on-chip flow and workloads are managed by a central shader and controller, and we have two supporting units, a general engine, which contains vector units for processing and optical flow, and a sort unit with comparators to handle the depth sorting and generate sparse masks. And the key hardware module in our design are the compute engines and buffers. To manage data efficiently, we designed two on-chip buffers, the novel CAN-based dual-index Gaussian buffer CGB for Gaussian parameters and their gradients, and the image and loss buffer. The forward engine group and the backward engine group are highly pipeline compute cores for rendering and backward rendering. And our hardware supports two distinct data flows. The first is the frame level pipeline, which is used for frames ready to generate a new accurate loss mask. And in this mode, first, the Gaussian parameters are read into the FEG to perform a forward rendering. And after the entire image is all computed, the solid unit then calculates a new sparse mask from the resulting loss map. And finally, based on the loss and its mask, the BEG executes the backward gradient propagation, and you can see from the pipeline, these stages form a traditional sequential pipeline. And however, for the frames with a predicted sparse mask, REACT3D switched to a broad level fused data flow, and two key changes happen here. First, the hardware processes the image block by block, guided by the predicted mask. And second, the FEG calculates the gradients applied and bypasses them directly to the BEG, which can then immediately start backward propagation for that block. And the result is clear in the timeline, and the forward and backward pass for each block are now tightly overlapped, achieving high hardware utilization. And let's take a closer look at our compute engines, which have a three-level hierarchy design. And at the top level, the forward and the backward engine groups are designed to process independent 16x16 pixels in parallel. And within each group, individual engines work on 4x4 subblocks, and this engine operates synchronously. A synchronization is broadcast to all of them at the same time, and the engine processes in parallel for its own pixel. And in the forward engine and backward engine, the forward engine itself is the big pipeline that processes a stream of Gaussians. It includes the data units for each step, like the alpha combination, the transmittancy update, and alpha blending. And it also fills the L1 nodes and gradient calculation directly to the end of the pipeline. This stream design can achieve high throughput for the rendering calculation. And similarly, the backward engine is also a big pipeline that processes Gaussian gradients in the reverse order of the forward pass. And it contains units to calculate the gradients of alpha, color, and other Gaussian features, ensuring just as efficient as the forward pass. And finally, let's discuss our hardware solution to the dual-index problem, and it's built around the content addressable memory, or CAN. which has two working modes: the standard address-based indexing and the content-based matching, where we can find all entries that match a specific data value. So this brings us to our CDG design, as the diagram shows from right to left. And we use SRAM to store the primary key and the future data and the attributes, and the secondary index is managed by a CAN. Furthermore, we deploy an auxiliary buffer to keep track of the stored secondary indexes. So in common stages, the CDGP operates in a normal address-based mode to ensure continuous access by the primary key. And in the sorting and merging stage, it switches to the content-based mode, which uses the secondary index for efficient CAN matching and sequential access by the secondary index. So in the sorting stage, it allows us to group data by PID before writing back to DRAM and convert this scattered writes into continuous memory size. And it can also leverage the sparse mask to skip write back of unnecessary blocks. And in the gradient merging stage, it allows to reorder the complete sequence to accumulate the gradients for the same GID sequentially, which animates the write confirmation. And finally, let's move on to the experimental evaluation of REACT3D. So for our experiment side, we integrated the performance simulator of our accelerator into the model GSM system. And for the hardware baseline, we compared with GSM-oriented GPU, GSR, and GPU online things. And our hardware was synthesized using a 12-nanometer CMOS technology. And as the table shows, the forward and backward engine consumes the majority of area and power as expected, and our CAN-based buffer consumes an acceptable portion of the resources. And first, for the reconstruction quality, as you can see from the visual comparison, our REACT3D at various sparsity levels maintain high visual fidelity, looking similar to the original dense version. And the quantity table at the bottom confirms this. We compare the PSMR configuration against original dense model and other baselines across all things, and our methods achieve the lowest average error of only 4.15%, whereas it's significantly better than both GSR and GPU. This proves our specification algorithm effectively preserves the mapping quality. And now for our main performance result, the top graph shows that the throughput in the frames per second. The red dashed line marks the 30 FPS real-time requirement, and as you can see, only REACT3D consistently meets or exceeds this target across all things. On average, we will achieve at 12.10 times, 3.91 times, and 2.23 times of the GPU, GSR, and GPU. And the bottom graph shows the energy efficiency normalized to the GPU. Here, REACT3D achieves an average of 24.18 times, 2.37 times, and 3.15 times over the GPU, GSR, and GPU. And to understand how we achieve this speed up, we come back to an average start. And this chart shows the incremental benefit of our key contributions. We started with a baseline accelerator that implements the original pipeline and a customized render unit, which already provides a 2.78 times speed up over the GPU. And then adding our specification algorithm gives a massive of 3.08 times speed up. Next, adding our fuse data flow provides an additional of 1.19 times speed up, and finally with the CDG design, it provides another 1.18 times speed up. Together, this co-design optimization results in our final overall average speed up of 12.10 times, which meets the real-time requirement of STEM applications. So that's all of this presentation, and thanks for your questions are welcome.
Any questions? You can come up to the microphone. So I noticed in one of your midway slides, you showed the timeline of the front to back blocks. And this pipeline, there's a lot of space. Yes, there's a lot of space there for the locks. So is there any opportunity there to either save energy or can you rebalance this pipeline?
So here, I think the pipeline is quite balanced because we use the pipeline design for the FEG and BG, so their workload
questions, come up to the microphone. Okay, let's thank the speaker again.